Okay, I ran out of time on the previous screencast. So, we were at the point of defining epsilon. And epsilon is a factor that tells us the dependence of the number of moles in the system on conversion. And based on what's written here, we have delta, which is the net number change in the number of moles in the system per mole of A consumed. And we have the mole, basically the mole fraction of A entering the reactor. So epsilon can be defined as delta, the net number change in the number of moles per unit of A consumed, times the mole fraction of A entering the reactor. And that's the easiest way to write the net change in the total number of moles. So if pressure and temperature are constant, we can write volume as the initial volume times 1 plus epsilon times conversion. Now, in general, maybe the pressure and temperature aren't constant, in which case the concentration will depend on those for a gas. So the most general expression we can write for the concentration of a gas in a reactor is the initial concentration of species A, so this a reference compound, over 1 plus epsilon times x. So that expresses how volume is changing due to reaction. That's multiplied by theta for that species minus the stoichiometric coefficient over that of A times conversion. So we always need this expression because it has to do with conversion and how you've changed the concentration. And then we have P over P naught times T naught over T if pressure or temperature changes. And we can plug these into conversion-based design equations and design reactors. One of the things that isn't quite worked out in this formulation is what happens if there's a phase change. So if there's a phase change, there might be a volume change, and we can account for that in the value of delta that we use. So for example, if there's condensation or chemical vapor deposition, there will be a saturation partial pressure, meaning that once the concentration of that species in the gas phase reaches that mole fraction, it's going to condense. And so if we have A and B being gas phase species that react, and they produce one gas, which is C, and D, which is either a gas or a liquid, depending on whether it's reached the saturation concentration, we can write the flow rate of D as FA naught times X. So basically we just produce D at the rate we would expect to produce it, as long as the mole fraction of D is less than the saturation mole fraction. And if we exceed that mole fraction, then the flow rate of D coming out of the reactor remains constant, and the rest is left behind either as a liquid or a solid in the reactor. And delta needs to be modified accordingly. So the stoichiometric coefficient is 0 for YD greater than YD saturation. And that's how we would change what happens. And that's the end. So I only had a little bit more to talk about as far as doing design with an extent of reaction.